Yeah, good morning, everyone. Welcome to Heidelberg, as Anna already said. Yeah, welcome to the Basic Attack and Mitigation Strategies presentation from Raphael and me. Before we start, just a couple of words on our side. Yeah, who we are just two networking geeks working for ERNW. We have a passion for IPv6, and I'm working with IPv6 for the last, I think, 6 or 7 years, not as long as Enno, because he's just older than me. So when he started working on IPv6, I had other interests than IPv6, but since a couple of years, I'm doing basically nothing else besides IPv6. Yeah, and welcome to the Basic Attack and Mitigation presentation. With me is Raphael. He was a long time in my team, now switched, but he is also responsible for IPv6 at ERNW, and so we are doing the presentation together. So, without further ado, let's just start when this thing works now. So, well, this presentation is split in 3 parts. The first part, at least, may be a little bit boring. I'm fully aware of that. It's just a little IPv6 refresher. I think we all should know how IPv6 works, just to make sure that everyone is on the same boat. We are just doing a very quick IPv6 introduction, just to make sure we are on the same page. So then we have a look, okay, why is IPv6 security actually so hard, and what are the actual problems? In part 2, we are looking at specific attacks on the local links, and then we'll have a look, okay, how we can mitigate those attacks. And part 3 is covering, which is Raphael doing, about scanning and reconnaissance, and a special attack called neighbor cache exhaustion. So, as I said, just a quick refresher. I'm fully aware that it might be a little bit boring, but we will do it anyway. So, but why isn't this working as expected? Come on. So, yeah, if you haven't done any work in IPv6, you might come to the conclusion, yeah, IPv6, I mean, it's 2015. The first RFC for IPv6 was dated back in December 1995. So we have this year our 20th anniversary for IPv6, and you may come to the conclusion, well, IPv6 is a well-defined set of standards, completed standards, but as soon as you dig a little bit deeper into the IPv6 topic, you will see, well, that's not necessarily the case. There are still quite some debates about fundamental functionality of IPv6, and we are attending quite a couple of IETF meetings, and inside these IPv6 related working groups, they are spending quite a lot of time discussing, okay, how can we modify some protocol behavior, for example, neighbor discovery. The last IETF meeting I was attending was last year in London. And they had a 1-hour slot, and 45 minutes. They were they were talking about just, okay, how can we modify neighbor discovery so that it works better, add more functionality. And so there are quite a lot of RFCs, both in the standards track, informational, floating around in the IETF space, which doesn't make it any easier from a security point of view, because you do not have any predictable behavior of a certain IPv6 stack in any given or in any given entity. And depending on the vendor you are using, some stuff may be implemented completely differently. And this makes it even harder for security, as at least in the terms of security, you want to have predictability so that you can predict how a device behaves when it, for example, receives a specific packet, which unfortunately isn't necessarily the case nowadays. And during the mid-90s, there was a complete different thinking of networking and security in general. But IPv6 was developed under some specific design paradigms. One big design paradigm was the end-to-end principle, network transparency. Network address translation was never planned, and there's still big debates inside the IETF working groups. Do we need network address translation in the IPv6 world or not? I think, no, we don't. Get rid of NAT. Yeah, I know it's a necessity in the IPv4 world, but the only reason we use it because we have just not enough IPv4 addresses. And we have this issue in the IPv6 world, so why should we use such crappy technology in the IPv6 world? Just get rid of it. And IPv6 was supposed, or is supposed to be used on a large scale. Sorry for the buzzword, the Internet of Things. All things connected to the Internet. This doesn't work with IPv4, and we have to rely on IPv6, which is a good thing. And IPv6 is supposed to be used by devices not running in well-managed networks. What does this mean? Well, even IPv6 should work even without a network administrator. So when I plug in my system into any given network port, it just should configure it completely automatically, and then I should be good to go. And IPv6 devices may be limited for their processing and configuration capabilities. Here are just some examples: smart meters, fridges, sensors, whatever. But these are some important design paradigms which you should keep in mind just to get a better understanding why some things were developed how they are today. So then we have, of course, our normal IPv6 header. There are some differences to the IPv4 header. For example, it is the size is 40 bytes and not 20 bytes like in the IPv4 world. There are some fields which are not present in the IPv6 header, which were in the IPv4 header. But besides that, we have our version, we have our traffic class, which is used for quality of service. We have our flow label, which isn't used today by any application I know of, but maybe in the future. We have our payload length. We have, of course, our hop limit, which is the equivalent to the TTL field. And we have, of course, the source address and the destination address, which is not 32 bits like in the IPv4 world, but 128 bits in the IPv6 world. So, and they thought when they developed IPv6, yeah, well, it may be a good idea to just put the necessary header information in the actual IPv6 header, and everything else just put it in optional extension headers. So let's say, for example, when I need fragmentation, as we can see here, we do not have any fields in the normal IPv6 header in regards to fragmentation, because I said, well, fragmentation is optional in the IPv6 world, and so when fragmentation is needed, just we put all this information in these extension headers, and then when the packets get fragmented, a fragment header is placed before the actual IPv6 header, so that all fragment-related information is stored in this extension header. In theory, this sounds good. In practice, and from a security point of view, it's just a mess. Because the RFCs failed to specify an upper limit of how many extension headers can be on a given IPv6 packet. So from a standards point of view, an IPv6 packet with, for example, 100 extension headers is totally valid, but of course there isn't any use case for that. The second thing is there is a recommended order how these extension headers should, RFC terminology, should appear inside the packet, but every host has to process the packet even though the recommended order or with extension header which are not in the recommended order. And we have done quite a lot of research in regards to extension header and the processing of intermediate devices, routers, firewalls, IDPS devices, how they behave with packets with many extension headers in different combinations. We won't cover these topics in this workshop, but if you're interested in this stuff, be here in the afternoon. Raphael and Antonius will give you an introduction to how you can evade IDPS devices in the IPv6 world with the clever use of extension headers. But from a security point of view, these extension headers are just a mess. But from a theoretical point of view, it sounded good at a first glance. So, yeah, as we might all know, IPv6 is a 128-bit address in the hexadecimal digits, so no decimal, and 128 bits. So it makes it quite hard to read just for the human eye, and we do not have any subnet mask anymore. We just have the CIDR notation, classes in the domain routing, as we can see here, and this just specify, okay, this is just a 40-bit prefix. And just to make it more readable for the human eye, we have some abbreviations which we can use to compress an IPv6 address, because nowadays there are quite usually many zeros inside the IPv6 address, and there are some abbreviations allowed to compress this IPv6 address. So the first simplification which you can do is you just can omit the leading zeros in each hex combination. So here in these 16-bit word, we have omitted the first three zeros to make it more readable from the beginning, from this IPv6 address to this one. And the next abbreviation which we can use is that we can summarize or replace consecutive zeros. Like these three 16-bit words can be summarized to colon, so that we, starting from this IPv6 address, in the end we have this one, which makes it more readable for the human eye. But all three of these examples are a valid textual representation of an IPv6 address, which where now we have the next problem. How does your security device, whatever, store an IPv6 address, for example, in a log file? Does it use this notation? Does it use this notation? Or does it use this notation? Well, that depends, and you have to double check. So it's not as easy like in the IPv4 world, when you have a log file and just make a grab over it to find an IPv4 address. In the IPv6 world, you have to think about, okay, how does the IPv6 address gets represented? And you have to cover all these possible ways to represent an IPv6 address. So to cover all these cases, you have to use a little script to find the IPv6 addresses, depending on how the actual device is using them inside the log files, which is unfortunate, but we have to deal with the situation. The IETF is also aware of that, and they released RFC 5952, which just gives some a recommendation how an IPv6 address should be represented in log files or in general text representation. The problem is, as the RFC already has in its name, it's a recommendation. I mean, it's in the standards track, but whether or not a vendor implements this recommendation, it's totally up to the vendor. So when the vendor is a good one, then he will obey to these rules, but he does not have to. So coming to the address space, we have a couple of different address spaces. We have the 2000:/3, which is just the global unicast address space. We have so-called unique local unicast address, which are more or less the equivalent to private IPv4 addresses. So these addresses should not be routed in the global IPv6 internet. But as the name already implies, even though they are used as private IPv6 addresses inside the organization, they should be unique, so that you do not run into the problems we have in the IPv4 world. When you have, for example, mergers and acquisitions, you bought a company, you have to connect the IT departments, and they are using both the same IPv4 subnet, so you have to rely on network address translation so that they can communicate with each other. In the IPv6 world, even if you're using unique local unicast addresses, this shouldn't be the case, ideally. If this turns out to be true, this has to be proved. But this is the intention of the unique local unicast addresses. Even though that they are private IPv6 addresses, they should be unique. But there is an algorithm which generates a specific prefix, but nobody hinders you to use just a unique local prefix which you assigned by yourself. So there may be circumstances where you have overlapping unique local addresses. But I haven't seen any environment where this happened, just because the deployment of unique local unicast addresses is very low at the moment. But we'll see how this turns out in the future. So the another address space which we have is link local unicast addresses. As the name already implies, every IPv6 enabled system generates this link local unicast address by default, and this address can be used to communicate with IPv6 hosts which reside on the same subnet, layer 2 domain, VLAN, whatever. So even though you do not have IPv6 deployed in your corporate environment, for example, as soon as the IPv6 stack is activated and two IPv6 enabled clients are residing on the same subnet, they are able to communicate over this link local address. And the fourth one is multicast. As you may know, IPv6 heavily relies on multicast-based traffic, so there are no broadcast addresses anymore like in the IPv4 world. There is a special multicast address, which is more or less a broadcast address in disguise. It's FF02::1, which is just it's called the link local all nodes multicast address. ::1, link local, all nodes, which, as I said, is just a broadcast address in disguise, because as the name already implies, every IPv6 enabled host has to join this link local multicast group, and if I send a packet to this multicast group, the system receiving the packet has to at least process this packet. So from a technical point of view, it is a multicast address, but it is a broadcast in disguise from my point of view at least. Yeah, then we have, as I already said, some addresses and their scope. We have a node local scope. We have, of course, a loopback address in the IPv6 world. In the IPv4 world, it was represented by 127.0.0.1 typically. In the IPv6 world, it's just : :1. We have our link local addresses. Then we had for a long time something called site local addresses. These site local addresses are deprecated as of now. And the successor to these site local addresses are the unique local addresses. Then we have our unique local addresses. And we have, of course, our global addresses, globally routed and reachable. And they are more or less equivalent to the public IPv4 addresses, which we know from the legacy protocol. So typically the standard, I'll call it prefix size or subnet size in an IPv6 world, is 64 bits. So the first 64 bits are the network identifier, and the last 64 bits are the interface identifier. There are a couple of ways how this interface identifier gets configured. You can, of course, configure your IPv6 address on your system static, like in the IPv4 world, or use some automatic mechanisms implemented in IPv6. The first mechanism was EUI64, which stands for Extended Unique Identifier. Basically, what is done, the host takes this 48-bit MAC address and fills up 16 bits to get the 64 bits, so that he has the 64 bits for the interface identifier, and then he has this 128 bits address. But you can, of course, rely on DHCPv6 as well. Same procedure, more or less, as in the IPv4 world, with one exception. In the DHCPv4 world, we were able to distribute default router information to clients, which isn't the case in the DHCPv6 world. You are not able to distribute any default router information over DHCPv6. You have to rely on another mechanism so that the clients get their default gateway, which I will cover in a couple of minutes. But from an address assignment point of view, you can use DHCPv6 like in the IPv4 world. Then we have the so-called privacy extensions. Privacy extensions were developed a couple of years ago as an improvement to EUI64, because when you're using EUI64, you have the problem that regardless in which IPv6 network you are connected, you will have the same interface identifier every time, because the client is just using the 48-bit MAC address, which typically does not change, besides you are switching your network interface card. So they said, well, yeah, that's not that good, because we could maybe get tracked, because we have, regardless of the IPv6 network we are in, we will use the same interface identifier. So the IETF came up with another approach to configure this interface identifier, which is called privacy extensions. Basically, the interface identifier is not derived from the MAC address, but a special algorithm, which is specified in the RFC, is used to generate a random interface identifier. And in addition to that, the client using privacy extensions is generating a second address. This second address is the so-called temporary address. And this temporary address will be used for every communication initiated by my client. And this temporary address has a short lifetime, so that this address gets changed. I think the default value are 1 day or 7 days, I'm not 100% sure. So the intention is, okay, when my client initiates a connection to any given system, he is using the temporary address, and after 1 day or 1 week or whatever time frame, he will generate a new temporary address, which he will use for every communication which is initiated by this client. In theory, this sounds good and addresses these privacy-related issues which EUI64 brings with it. But from an enterprise or corporate point of view, it's more or less a pain in the ass. I'm sorry for that. But because when you think about filtering, you will have a hard time implement ACLs or firewall rules for clients which are generating a new address which they're using for outgoing communication every day. And just that you get an idea how this looks like, as we have here fully dual stack network. As you can see here, that's just my Wi-Fi interface. And as you can see here, my Windows 7 client has generated two addresses, two IPv6 addresses from a given prefix. I would call it the public or standard IPv6 address, and then the second address, the temporary address. And as we can see here, up until the 40, that's the network ID, and everything after the 40 is the interface identifier. And my client will use this temporary address as source address for every communication the client initiates. So let's say, for example, when I issue a ping, which I should already have running, we should just Just have to fire up Wireshark very quickly. So as you can see here, I'm pinging some IPv6 systems, which is just Google. And I'll just stop that for a minute. So as we can see here, the source address my client is using is the 23E or 23E1. Having a look back to the interface configuration, we see now that the 23E1 is my temporary address, and this address has a shorter lifetime than the IPv6 address here, which we can see when we issue a specific command. Yeah, as we can see here, we have our normal public address and we have our temporary address, and as we can see here, the public address has now a valid lifetime of 30 days, which are just the default values used on the Cisco routers for the lifetime when they're sending router advertisements. And we have the temporary address. In this case, it was 7 days. And after these 7 days, the client generates a new temporary address, which he then will use as a source IPv6 address for every communication, for every outbound communication. But my client is, of course, reachable over both addresses, the public as well as the temporary. So if I would have an SSH server active, I could use both addresses to initiate the SSH connection. But for every outgoing connection, he will always use the temporary address as a source. No. Yeah, and then the last approach in regards to interface ID generation is RFC 7217, defined or developed by Fernando Gont, who is also here at the IPv6 Security Summit. Basically, RFC 7217 describes the so-called stable privacy addresses. So the basic principle is that the client, once it joins an IPv6 network, it configures a random generated interface identifier, but this random interface identifier is stable as long as the client is connected to this IPv6 network. So if I leave the network and join another network, he will generate another interface identifier, but as long as I will be part of a specific network, this interface identifier will not change, so that I have a stable IPv6 address inside a given IPv6 network, and that my client is not generating a new address every 7 days. But I'm not aware of any operating system which already implemented these privacy or the stable privacy addresses, but at least from my understanding, it should be just a matter of time until this happens. But I haven't seen an operating system. If you know more, I would be happy to hear it. But these are the different mechanisms which can be used to generate the interface identifier. Yeah, this we already have spoken about, the EUI64 and the random generated value, the privacy extensions, meant to counter address scanning and hiding the identity, and is the default on every Windows-based operating system, starting with Windows Vista. And depending on the actual Linux version, it is nowadays, I think, the default, at least for Ubuntu and some other couple of Linux systems, where they also use the privacy extension as the default mechanism to generate the interface identifier. Come on. Why don't you work like you should? So that's about it. The IPv6 address or interface ID generation. So the next important protocol is IPv6. In the legacy protocol or IPv4, technically we could survive, or IPv4 would function without ICMP, but it was an important protocol, especially for troubleshooting purposes, just to verify connectivity or to communicate error conditions to a receiving host. This has fundamentally changed in the ICMPv6 world. Without ICMPv6, IPv6 is not working at all. One reason for that is in the IPv4 world, we had a separate protocol which was responsible for the resolution of an MAC address to a given IP address, which was ARP, Address Resolution Protocol. In the IPv6 world, we do not have ARP anymore, and the functionality of ARP was integrated into ICMPv6. So there's two special ICMPv6 messages which are just responsible for the so-called neighbor discovery, which I will show you in a minute. And they included some other functions into ICMPv6. For example, when you're doing multicast-based routing, you had in the IPv4 world a separate protocol, IGMP, which was used by clients to tell the router, dear router, I want to receive the multicast-based traffic for group X or Y. And this functionality was also now implemented into ICMPv6 based on MLD, Multicast Listener Discovery. Essentially, it is working as in the IPv4 world, but it's not a separate protocol anymore. It is realized over ICMPv6, and in this special case, over the Multicast Listener Discovery protocol. Yeah, and as I said, ICMPv6 is an integral part, and without ICMPv6, IPv6 just does not work. So here's just a quick list of some main ICMPv6 type, some of them which we will cover later on. We have, of course, some destination unreachable, same behavior as in the IPv4 world. Then we have the packet-to-big ICMPv6 message, which, at least from my point of view, is one of the most important ICMPv6 messages. Why? Because, as I said a couple of minutes ago, fragmentation is only optional in the IPv6 world. And what does happen in the IPv4 world when a router gets a packet and the packet is bigger than the MTU where the packet has to be transmitted? What does the router do? Yeah, he fragments the packet. So in the IPv6 world, a router will never fragment a packet. When fragmentation is needed, the source has to fragment the packet, and the destination has to reassemble these fragments. But a router will never fragment any given IPv6 packet when in the IPv6 world. So, but what happens now when the router receives an IPv6 packet and the packet is larger than the MTU size of the link? He discards the packet and sends an error message back to the source indicating, well, I received a packet from you, but the packet is too big, please fragment it. And this is realized over the packet-to-big message. So you should always allow this ICMPv6 message. If you have a security policy in the IPv4 world, which just denies every ICMP communication, you should think about it in the IPv6 world. At least you have to allow the packet-to-big message just to make sure that IPv6 is working. Otherwise, you could run into connectivity issues, because when the client does not know that he has to fragment the packet because the packet gets filtered, the connection to the destination can just be established. Yeah, then we have our echo request, echo reply, same thing as in the IPv4 world. we have 3 MLD-related packets: the query, the report, and the done message. The query message is sent out by the router to find clients connected to a local link, which are a member of any given multicast group. When a client receives a query message, he answers with a report message, so that the router knows, okay, on this link there are clients member of multicast group X, Y, and Z. And then we have the multicast listener done message. When a client wants to leave a specific multicast group, he just sends a done message to the router, so that the router knows, okay, there's a client who wants to leave a given multicast address. So then we have 2 new ICMPv6 types, which we hadn't in the IPv4 world, so-called router solicitation and router advertisement. In the IPv6 world, a client where IPv6 is enabled tries to find a router on the local link. Excuse me. So, how does he do that? Well, he just sends a router solicitation. Just basic. Put it here so that you can see it better. When we have just basic setup, we have our router, we have our switch, and we have a client connected to it. As soon as the v6 stack gets initialized, the client configures this link local address, and he tries to find an router, which he tries to find by sending a router solicitation. He sends this router solicitation to a special link local multicast address. Where have I put this blue one? There. Thanks. And this multicast address is called ff02::2, and this is the link local all routers multicast address. And as the name implies, every forwarding device has to join this link local routers multicast address, so that when a client sends a router solicitation destined to this link local multicast address, the router gets the packet, processes it, and answers with a router advertisement. So router solicitation comes in, and the router responds with a router advertisement, or short RA. And this router advertisement is sent to this link local address, multicast address, just to make sure, even though one client sent the router solicitation, the router said, well, there may be other IPv6 clients on this segment which want to know the information stored in the router advertisement. So instead of unicasting the packet to the actual source, he is sending the packet to the link local all nodes multicast address. So to ensure, okay, that every client connected to this segment is receiving and processing the router advertisement. So, and this is a process new to the IPv6 or new to IPv6, and this is done every time a client or the IPv6 stack gets initialized. These router advertisements are sent in response to received router solicitation, but they are also sent periodically in a specific configurable time interval. Here in this environment, I have put the interval pretty short. I think it was 4 seconds. So every 4 seconds, the router is sending the router advertisement to this link local all nodes unicast address, just to make sure when a new client connects to the network that he will receive the router advertisement pretty fast, so that he can configure the IPv6 address, for example. And maybe we have luck and we see that. Nope, that was the wrong one. The problem, it isn't a problem. But as we can see here, we haven't seen any router advertisement. The reason for that is that our wireless LAN controller is filtering these periodic router advertisement. Now you could ask yourself, okay, why is he filtering that? Because sending a router advertisement every 3 seconds over the Wi-Fi connection to every client wastes a lot of airtime. So what does the WLC do? He has so-called router advertisement throttler, so that he will let pass a router advertisement once every 30 minutes. But when a new client joins the network and he sends a router solicitation and the client and the router sends the router advertisement, he will get through. But as we have here our wired connection, do we? So, oh well, just no. No, it's okay. As we have here our lab network, which is not connected to the actual conference network, but the behavior is still the same. So we should see ideally router advertisements. No, we do not. Interesting. Yeah. So this looks better. So links get initialized, and as we can see here, we see our router advertisement. The resolution is horrible. So, and as we can see here, there are quite some information stored in these router advertisement. On the wired side, these router advertisements are of course not throttled in any way. So when you are connected to the wired network, you will see the router advertisements every 3 seconds. And we can see a couple of information which are transported in the router advertisement. As we can see here, we have the prefix information. This is the mechanism so that the client knows, okay, which actual prefix is on that local subnet. And as we can see here, it's 2A02, 80, yada, 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 /64. So my client parses this information and configures an IPv6 address from this prefix based on the privacy extensions which we discussed earlier. And as we can see, here's now my wired connection. As soon as my client gets this router advertisement, he knows, okay, the network identifier are these 64 bits. So I'll continue and configure my interface identifier based on the privacy extensions, so that my client, so that he has an IPv6 address and connection. And the second thing we see now is that we now have a default gateway, FE80::1. And this default gateway gets installed because my client receives a router advertisement. Because the logic inside the client as well, I received a router advertisement, so it should come from a router, and I should use him as a default router. So there's no special option inside the router advertisement which specifies, okay, please install this router as a default gateway. My client implicitly configures this link local address as his default gateway, which, as you can see here, this is our valid router. He is sending from the source FE80::1, and my client is installing or is using this link local address as his default gateway. Then we have a couple of other information here, DNS servers, IPv6 and IPv4. And we have actually, here in this network, we have two mechanisms to provide the clients with a DNS server. The problem is for a long time, it wasn't possible to distribute DNS server information over router advertisements. But this has finally been fixed, and the IETF released an RFC 6106, which enhanced these router advertisements so that I can insert recursive DNS server information, which I have done. Luckily, we are using an up-to-date image on our core router, which supports this feature. Problem is, the normal or current client operating system, at least in the Microsoft space, do not support this, this information. So even though it is installed or it is inside the router advertisements, at least Windows clients do not process this information. So in order to get a Windows-based client, the DNS server information, we have to rely on DHCPv6, which is called in this scenario the stateless variant. Because we do not distribute IPv6 addresses over DHCPv6, the only reason we are using DHCPv6 is to distribute DNS server information to the clients which are not able to parse these DNS servers provided in the router advertisements. It depends on the operating system whether or not this can get or this option is supported. At least in the Windows space, it isn't. I'm not 100% sure whether Microsoft will include it in Windows 10, but as far as I know, they won't. They say we have DHCPv6. When your clients want to have DHCPv6 DNS servers, please use DHCPv6. Yeah, and then we have the source link layer address, which is just the MAC address of the router, so that I have an association between the link local address, the FE80::1, and the source link layer address, which is then stored in my neighbor cache. And this is the only mechanism which can be used to distribute default router information to the clients. You do not have, as already said, any possibility to distribute default router information over DHCPv6. There was quite a lot of discussions a couple of years ago inside the IETF. Well, should we provide the default router information over DHCPv6? There was a draft version issued by the IETF, but at least for 2 or 3 years, no work was done with this draft, and the draft already expired. So do not expect that this option gets implemented into DHCPv6 in a reasonable time, which is quite unfortunate from my point of view. Speaking from a corporate network administrator point of view, you now have to rely on 2 mechanisms to provide the clients with a full configuration. You have to rely on DHCP, at least for the DNS server information, and you have to rely on router advertisements to provide the prefix information when you're using the router advertisements for the prefix for the interface generation, and for the default gateway, which is unfortunate, but we have to deal with the situation. And I'm not sure that this will change at all. So, and then the last 2, neighbor solicitation, neighbor advertisements. These 2 packets, or these 2 ICMP packets, are used for the address resolution. So from current slide, yes. So basically, the neighbor solicitation is the equivalent to the ARP request, and the neighbor advertisement is the equivalent to the ARP reply. Sorry for that. Huh? Ja, machen wir dann eine Pause. So basically, when two IPv6 clients are connected to the same link and they want to communicate with each other, they of course need to have the MAC address of the destination. So when we have Alice and when we have Bob. What they basically do is Alice wants to communicate with Bob. Alice has the IPv6 address from Bob, but not the MAC address. What Alice is doing is it sends a neighbor solicitation to a specific multicast address. And Bob is answering with a neighbor advertisement. And this neighbor advertisement includes the MAC address of Bob. And so Alice has every information she needs to initiate the communication. And the address resolution is done and performed over these two IPv6 types. Yeah, the neighbor discovery protocol, which we discussed now, has a couple of tasks. Router discovery over router solicitation, router advertisements, prefix discovery, address auto configuration, duplicate address detection is another mechanism. Of course, when an IPv6 client configures an IPv6 address, it has to make sure that this IPv6 address is unique. Otherwise, you run into issues with duplicate IPv6 addresses. Same problem as we have in the IPv4 world. Yeah, and the address for the address resolution, we have the neighbor solicitation and then the neighbor advertisement. And when this process is done, both nodes update their so-called neighbor cache. The neighbor cache is more or less the equivalent to the ARP cache, or it's a funky ARP cache more or less. So that I have a local cache where I have the association from a given IPv6 address to a given MAC address, which I can, of course, have a look at. As you can see, it's not so easy as in the IPv4 world, where you just do ARP-A. You have to rely on NetSH interface, IPv6, show neighbors, and what we see here is on my wired connection, as we can see, I have a couple of multicast addresses, but the only other entry in this cache is for my default router, FE80::1. There is the association to the physical address, which was provided from the router advertisements, and the type is reachable. So when I want to ping FE80::1, I do not have to do the neighbor resolution because I have all information I need to construct the layer 2 frame. Yeah, neighbor solicitation goes out to a specific multicast address. Bob processes the packet, answers with a neighbor advertisement, both update their neighbor cache, and then they're all set and can communicate with each other. So, and this mechanism is also used for the duplicate address detection. Let me see if we have seen it here. Yeah, here we can see it. We see a packet with a source address : This is a special address which is used for the duplicate address detection. What we see here now is the target address. This is the address my client wants to configure for his interface. But before he can use this IPv6 address on the interface, he has to validate that this IPv6 address is unique, so he can't use it. So in order to ensure, okay, nobody else has this IPv6 or link local IPv6 address, he uses the source address : which is the so-called unspecified address. And the destination is a special multicast-based address which corresponds to this target address. And when my client does not hear anything or does not get a reply, he thinks, okay, I am the only one who has this address, and then he subsequently is using this address. As you can see here, he is waiting not very long. How much is that? Not 1 millisecond. He's waiting for an answer, doesn't get an answer, and then you see in the next packet he's using this target address as his normal source address because the duplicate address detection was successful from the client point of view. And the same, of course, happens here. But as we can see here, it is for the global addresses. As soon as the client receives the route advertisement and has the prefix information optional processed, he continues to configure the interface identifier. And of course, he has to make sure that this global IPv6 address is also unique. And he's doing that by the same mechanism twice, because for the public address and for the temporary address. And as we can see here, after that, the duplicated address detection was successful, or the validation was successful, and then he's using this address as source. Yeah, and all these information, or this association between the MAC address and the IPv6 address is stored in the neighbor cache. And it's a little bit more fancy than the ARP cache in the IPv4 world. In the IPv6 world, the entries in the neighbor cache can have different states. The first state is incomplete. Incomplete just means, okay, I send out a neighbor solicitation to get the MAC address of a given IPv6 address, but my client hasn't received an answer yet. So reachable, as soon as he receives an answer, the state goes from incomplete to reachable, and then the whole point of these other states is that the entry in the neighbor cache does not time out. In the IPv4 world, if you do not have communication with the endpoint for a couple of minutes, the entry gets removed, and address resolution has to be performed when I want to communicate with this again. In the IPv6 world, they wanted, we should reduce the chatter for the neighbor discovery. So the neighbor cache entries have just different states. So what this basically boils down to is, even though these two communication parties are not communicating with each other, they are trying to reach each other to verify that they are still there. And if this is the case, this entry here will never time out, and he will go from reachable to stale, delay, probe, and then at the end of the day, as soon as the target is reachable, the neighbor cache entry will be in the reachable state and not gets deleted from the neighbor cache. Yeah, we already talked about it. The router discovery based on the router solicitation and the router advertisement messages to get to provision the clients based on the link local address, link local multicast address. The router is sending it to the link local all nodes multicast address so that Alice receives the packet and configures her interface identifier by herself. Yeah, and this we already talked about, the pass empty discovery. It isn't a new mechanism in the IPv6 world. We had the same mechanism in the IPv4 world, but in the IPv4 world it's just broken because many intermediate devices are just plain filtering ICMP packets. So pass empty discovery, at least in the IPv4 world, never works. But in the IPv6 world, it is necessary that it works. Otherwise, you will run into connectivity issues because the routers do not fragment the packets. They discard them and send an ICMP packet to big error message back to the source of the packet. If the source does not receive this error message, the source does not know that it has to fragment the packet, and the connection to a given end system cannot be established. So you should make sure that you have in your firewall rule set in regards to IPv6, you should have, or you must, in RFC terminology, you must allow these packet-to-big messages, otherwise you will run into problems sooner or later. So, and as we have seen, there are several types of auto-configuration. The stateless by means of the router advertisements. As we have seen, the router advertisement has some PIO, prefix information option, which we have seen. And as soon as my client processes this information, he starts to configure his interface identifier. And in the meantime, can also distribute other parameters like DNS servers. And this variant is called SLAC, stateless address auto-configuration, so that you do not have a central DHCP server for address assignment. The router just inserts the prefix information into the router advertisement, and the clients configure the interface identifier by themselves. But we can, of course, use DHCP-v6 for address assignment, which is also possible. Or we can use a hybrid mode, I would call it, or stateless with DHCP, where you, for example, use the router advertisement prefix information optional so that the clients configure their IPv6 interface identifier by themselves and are using DHCP-v6 just to distribute DNS server information, domain search list, or other DHCP options which are used for some specific use cases like voice over IP, wireless networks where you have to rely on specific DHCP options to get information to the phones where they find their call manager, or in the wireless space where the access point can find their wireless LAN controller. And these are the variants which you can use, but you always have to rely, at least in the corporate environment, on both mechanisms, router advertisement and DHCP-v6 to provide the clients with a full configuration. Yeah, and here we see what can be distributed by which mechanisms. Addresses can distributed by router advertisements and, of course, DHCP-v6. Default route can only be distributed by router advertisements, not by DHCP-v6. DNS resolver, in the meantime, can be distributed by both mechanisms. And, of course, all other DHCP-related options can only be realized with the use of DHCP-v6. And to determine what information a client should request from a DHCP-v6 server, there are actually two flags inside the router advertisement. One is the O flag, which stands for Other Configuration Flag, which basically tells the client, dear client, please go to a DHCP-v6 server and get other configuration information like DNS server or a prefix or a DNS search list, but not an address. If the M flag is set, this indicates the client, okay, dear client, please go to the DHCP-v6 server, get an IPv6 address and all other configuration information which the DHCP-v6 server has to offer. And this gets, or this is realized by these two flags inside the router advertisements. And when we have a look here in our setup, FE80::1, this should be, no, it is not. Here we have it. This is done here in the flags. And as you can see here, the M flag in our network here is not set because we do not use DHCP-v6 for address assignment. We only set the O flag just to indicate the clients, okay, dear clients, just configure your address by yourself and go to the DHCP-v6 server and ask for the DNS server, DNS search list, and so on. But these two flags will be used for that to indicate the client, okay, what information should I ask the DHCP-v6 server for? So, to summarize, yeah, we have quite a different mode of operation. We have different design goals which want to be achieved in the IPv6 world in comparison to the IPv4 world. And we have lots of flexibility introduced into IPv6. From a security standpoint, I'll let you decide whether this is a good or a bad thing to have this kind of flexibility. In some use cases, this flexibility is definitely good, but from a corporate or enterprise perspective, it may not be the best thing. So coming to the interesting part, the IPv6 security. Before we are talking about specific attacks, I just want to talk about, okay, why is IPv6 security actually so hard? This has a couple of reasons which I just want to present to you just so that you get a better feeling, okay, why is that the case? What we will cover the trust model and the modes of provisioning, which we already covered in the slides before. Then we will cover the so-called crypto optimism. We will cover complexity, the state problem, stack heterogeneity, and the attack and defense asymmetry. So the big problem is, as I said an hour ago, this year we have the 20th anniversary of IPv6, and we have different generations of IPv6 stacks for different functionalities, for neighbor discovery, address selection, and generation of the interface identifier, and so on. We have our initial RFCs, 1970, then we have 2410, 4861, 6980, yada, yada, yada. The problem is you do not really know, okay, which generation of IPv6 stack does your endpoint implement. So maybe he is using as an address selection algorithm is based on the older RFC 3484 or the updated version 6742. Or how does your client perform neighbor discovery? Is the neighbor discovery based on RFC 2410? Is it performed on based on RFC 4861? Or the generation of the interface identifier, EUI 64, privacy extensions, and so on. Point here is that when you try to get an idea, okay, of all your systems in your environment, it is more or less an impossible task to get an idea, okay, which generation of IPv6 stack gets or is implemented in all your devices running in your network. I mean, when you just have 20 or 30 devices, you can do that, but in large corporate environments with hundreds of thousands of hosts or IPv6, potentially IPv6 enabled hosts, it's impossible to figure out, okay, what kind of stack these devices implement, which makes predictability pretty hard, so you can't really predict how the systems behave when it gets in a specific IPv6 packet. Another problem is IPv6 trust model. Back in the 90s, they had a complete different thinking of security in general as we have it today. And the basic security assumption back in the 90s when they developed IPv6 was, well, the local link or the local network is trustworthy. So everyone in the local link, we are all brothers, everything is fine and dandy, and there will not be any attackers or malicious activities inside the local network. The problem is because of this reasoning, they didn't implement any security mechanisms in these basic features for address resolution or for the router discovery process. There aren't any security mechanisms which you can secure these operations because of this trust model on the local link. We are all brothers, which makes it, of course, harder to secure the local link or to defend against attacks on the local link based on the router discovery process or the neighbor discovery process. And that's a big problem. And Fernando Gont did a security assessment of the neighbor discovery protocol for IPv6, where he said, well, yeah, its increased flexibility implies a somewhat increased complexity, which is always bad for security, which has resulted in a number of bugs and vulnerabilities found in popular implementations. And in this RFC, he provides some guidance, okay, how or what options you have to implement a secure neighbor discovery process, and we will talk about it later on. Yeah, and we really like the idea, but it's just not feasible that that the local link, at least in most environments, is trustworthy in any case. But we have to deal with it, and we have to implement mitigation techniques to mitigate those attacks, which can be easily launched from the local network, which we will cover, I think, after the break. So, coming back to a router, because this is an interesting one as well. When you look up Wikipedia, what is a router? A router is a device that forwards data packets between computer networks. If you are reading 2460, the initial RFC for IPv6, the definition of router is a node that forwards IPv6 packets not explicitly addressed to itself, which is, of course, correct. But in the IPv6 world, a router is not only a forwarding device, it is also a provisioning device. Because RFC 2461 states, router advertises their presence together with various links and internet parameters, either periodically by sending the router advertisements or in response to a router solicitation message. So, in the end of the day, this means a router is just not a device forwarding packets. It is also a provisioning device as well. And we generally like the idea, but from an operational point of view, and having my network administrator hat on in large corporate environments, this isn't necessarily such a good thing because of the brilliant interaction or state of route advertisement and DHCP-v6 interaction that you have to use both mechanisms to provide the clients a full IPv6 configuration, which makes it more complex from an operational point of view, and complexity always impedes security. But we won't talk about it anymore, but this is just the current state which we have to deal with. Yeah, coming to the crypto optimism. Back in the 90s, as I already said, there was a complete different thinking of security in general. And back in the 90s, they thought, well, yeah, even if there are any security problems, we can address them with crypto. Well, as it turns out, yes, crypto may be a sufficient mitigation technique, but crypto has always an operational price tag. I mean, using encryption is easy, key management is hard, but this thinking shaped IPv6 because they said, well, we do not have to implement any security measures when we have IPsec implemented in the IPv6 stack. So when you want to do security, just use IPv6. In the meantime, the IETF revisited that statement and said, well, yeah, up until 2011, IPsec was a mandatory implementation for every IPv6 stack. With RFC 6484, I think, they updated the IPv6 node requirements, and IPsec is no longer mandatory, it is now an optional component. So depending on the generation of IPv6 stack, it may be possible that the IPv6 stack does not include IPsec. But in the 90s, they thought, okay, everything can be solved by math and some algorithms. And this thinking, as already said, shaped IPv6. For DHCP-v6 was complemented by RFC 3318, which defines an algorithm where a DHCP-v6 client and a DHCP-v6 server can be authenticated by means of a pre-shared key. Well, yes, this sounds fine and dandy, but in large corporate environments, you have to configure this pre-shared key on every client and, of course, on every server. And as soon as you have to change it, you have to change it on every client. And at least no DHCP-v6 server I know of does support this mechanism, and don't expect that it will used anywhere. It was implemented by, or it was developed by the IETF, but don't rely that it gets implemented by common DHCP-v6 servers or client operating systems. So another gem, send, secure neighbor discovery. They thought, well, yeah, there may be reasons where it could be beneficial to use cryptographic mechanisms to secure the neighbor discovery and the router discovery process. And they came up with this wonderful idea of send, where basically what the clients do is the following. They are, from a client perspective, every client has to have a public-private key pair, and the interface identifier for the address configured on the client is derived from this key pair to prevent IP spoofing or IPv6 address spoofing, and the router discovery process is secured by means of certificates. So this basically means we have our router advertisements, just to make it on a high level. And on this router advertisement, we have all these fancy certificate information. So the certificate is in the router advertisement. And only when the client is able to validate this certificate, he will process the packet further and the information stored in this router advertisement. Well, so this basically means you have to deploy certificates on every client, which you may already have for other functionality. But also, you have to deploy these certificates on your routers, and they have to use these certificates with the router advertisements. In theory, back in the 90s, this sounds great. Nowadays, from an operational point of view, forget about it. Don't rely that you will see send in any corporate environment, because the typical corporate operating system, Windows, does not support send. So you're out of luck in this case. For example, Cisco does support it, so you could technically configure it. In the Windows space, there is a third-party implementation by the Hasso-Plattner Institute. So you could theoretically use send in Microsoft environments, but it is so operationally expensive that, at least from our point of view, it's just not operationally feasible to use it in large-scale environments. So know that it was specified, but do not expect that any environment is deploying send in any reasonable way. But they thought, well, to address all these issues, we can use crypto by means of send. Yeah, then complexity. This was a very interesting statement. As I said an hour ago, the last IETF meeting I was attending was IETF 89 in London, which was last year, beginning of March. And in this IPv6 six-man group, the working group which is responsible for maintaining the IPv6 protocol, the first statement, the first guy on the microphone said, well, yeah, ND overspecified, and he is completely right. And that's the problem, because they are trying to squeeze in more and more features and functionality into the neighbor discovery process. The overall complexity increases, which of course impedes security. Yeah, and looking at the neighbor discovery RFCs in general. So the initial specification, RFC 1970, dated August 1996, 82 pages. Updated by RFC 2461, dated December 98, 93 pages. Obsoleted by RFC 4861, September 2007, a whopping 97 pages. And this is mainly considered the latest stable one, which is cited in most textbooks and if existent stack documentation. So, and here we can see a small excerpt from this RFC. And as you can see here, well, it seems to be quite a complex protocol, which is the basis for the whole IPv6 protocol suite, neighbor discovery. So now you could think, well, we could have reached a kind of stable state for the core mechanisms of IPv6. Well, unfortunately not. RFC 4861 was further updated by 5942, 6980, 7048, yada, 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 which basically boils down to that even though the protocol has its 20th anniversary, in this year we still haven't kind of reached a stable state for the core mechanisms of the next generation protocol. And yeah, in the V6 Ops working group, which is the IPv6 operations working group inside the IETF, they spent significant time on modifications of neighbor discovery. And I was following the webcasts from the more recent IETF meetings, and they were just basically doing the same further on, which, yeah, isn't that good from a security point of view, because we never get to a really stable state where we can say, okay, this is the core specification for core IPv6 functionality. They always try to squeeze in more and more or modify the behavior of core elements of IPv6. Yeah, just a quick look at RFC 6980. 6980 is from a security point of view, a long overdue RFC because it forbids the fragmentation of all neighbor discovery related packets. Why is this important? We will see that after the break. But it still adds complexity to decision taking and subsequently stack code. And this RFC was released in August 2013. And as far as I know at least corporate major operating system vendor does support it. But we will have a deeper look at this RFC when we are doing some attacks against some clients. Next big problem is attack and defense symmetry. The first, or due to the long warm-up phase, we have a huge asymmetry between attackers and defenders. The first IPv6 attack toolkit, which was developed by Mark Heuse, the THC IPv6 toolkit, was released in 2005, so 10 years ago. An RFC describing a feature called Router Advertisement Guard, which tries to prevent or to mitigate some attacks, which we will cover later, was released February 2011, so 6 years after that. So the attackers have an advantage of 6 years until the IETF, or in general, some people thought about mitigating techniques to mitigate common IPv6 attacks. And they are still not working sufficiently from our point of view, and probably never will, but my hope dies at last. I hope these features will work at some point, but we will see how these features work and how we can circumvent them after the break. Yeah, as we can see here, just an excerpt from the PACSEC security conference dated back in 2005, where Mark Heuse presented his tool suite, attacking the IPv6 protocol suite 10 years ago. Yeah, and last but not least, IPv6, as we now may know, is very different from IPv4, and so is IPv6 security. You cannot transform your IPv4 security model one-to-one to IPv6. You have, of course, to make adjustments and modification, and especially in regards to your filtering approach. As I already said, when you're filtering IPv6, then you will run into problems. So now I think we are on time. It's 11 o'clock. If you do not have any questions up until this point, I would suggest we are doing 15 minutes coffee break, and then we'll start with the next chapter.